Hi folks, this is Brendan Stanford for Comp 444, and this is the derived, I don't know if you can see it quite that easily, I might turn it this way. This is the derived or PD controller for a natural light. Now you can see right now it is oscillating between values in the 60s and the 40s, and 30s, but you can see once we get close to the boundary range, the oscillations still occur, but gradually they reduce in magnitude. So if I put, I don't know if you can see it there, but as I put it near the boundary condition, or sorry, the target domain, the oscillations decrease dramatically. Now outside that boundary condition, again, if we still cover the light, it's fully lit up, and we're still getting oscillations clearly. Likewise, if I shine a light, the light goes off. But these oscillations are reduced, especially when they're close to the set point compared to the proportional controller. And I'll show that one in a second there. So the main change in the program or the code is this section. So initially, the proportional code is just that you have the constant or a set constant for proportional control, but then the derivative term in the textbook was -1 times the gain times velocity. So in this case, I assumed velocity, the derivative would be the correction that initially would be output. That would be the system's initial response to light level. And then the error is the parameter, it's the gain, effectively, that's affecting the magnitude of change. So what this derivative term is doing is essentially it's accounting for what is the change, how will the response by the closed feedback system, how can you decrease the magnitude of its response to get within the boundary or within the set point and not wildly oscillate because of its own response around the set point. So that's the proportional controller again, or proportional derivative. And then of course to actually do the derived correction or the PD correction, you get the proportional term plus the derivative term. And so KD here is again that derivative constant. I actually zeroed in on, I kept the same value for the proportional constant from the last iteration, but I used a value of 0.1 for the KD, or the derivative constant. And then effectively the system is proceeding as it had before, but now it's going to emit the derived correction instead. And again, if the correction itself is less than 0, then the derived correction automatically will also be less than 0. So it will just change the output, the derived correction, to being light off. If it's above 255, that's the maximum light level. It'll just set the derived correction to 255. All right, and now as promised, so again, there's one last demo of, oh, that was an interesting response, the proportional derived controller. I'm just now going to switch it so you can see, for the sake of example, to my proportional light controller. I'll upload that one. Give it just a moment to get started. Still uploading. Hopefully I can fit this in time before my screencast time limit gets cut off. All right, and now check the serial monitor. Okay, it's outputting. So again, I can cover it, get full light. If I put light on it, no light. And here we can see the difference, because if I start to, even if I attempt to approach the set point of 40, I believe it is, the oscillate, it's still like, there's a difference certainly between when it's more shaded to less shaded, but it's still oscillating wildly. The oscillations aren't diminished by using the derivative, and so it's still naturally going to oscillate above and below the set point rather than honing in on it. All right, that was my proportional derivative controller. Last is PID. Again, Brendan Stanford for Comp 444. Thanks, everyone.